start. So our next speaker is Augusto Teixeira. He will talk about CLT for class of random walking learning environment.
Thank you. And thanks a lot to the organizers for the invitation, for putting together this amazing conference. Before my talk, I met Pierre and he said, oh, what an amazing work you're going to talk about. So I looked back at the title, maybe it's a bit clickbaiting, but you know, it's a class that hides the... We're going to restrict our attention to specific cases. But anyway, it's going to be fun. This is a joint work with Julian, who's just finished his PhD with Oriane, and Ranjan. We'll start with our setup. So in our general setup, for random walks in dynamic random environments, it's going to be taking place in D spatial dimensions and one extra for time. So we'll basically think that we are in ZD plus 1. We're going to fix a space-time environment that for simplicity is going to assume only two values today. So this for x in ZD and t integer, no negative integer. And with this we can define our random walk. It's gonna be, you know, at 0 almost surely at time 0, and it will jump to the right, given that it was at x before, with probability that depends on the environment. So, very similarly to Daniel's talk, I'm going to fix two parameters, P0 and P1 in 0, 1, that are going to determine these laws. Oh, sorry. Yeah, I started the talk with, yeah, let's put these laws. I changed the last time to any dimension. Yeah, let's fix two laws. P0 and P1 are laws on, and it can be even minus R to the D. Yeah. So if you want to give a jump to direction V, you do this with probability P1 of V if your environment at the position you were before, which I'm now calling P to X, at time T was 1, and if it was 0, you use the distribution P0. And here this is yeah, fully determining the jumps because these are semi-absolute. Okay, so we are going to make a small picture just to make it clear. The picture is indeed one-dimensional, so here's space, here's time. We start at 0, so we have probability P0 to go to the right, P1. Now I'm back to what I planned before. Let's say you jump to the right, so it's a kind of diagonal jump, right? Time is always passing. And here you jump with probability P1 to the right, 1 minus P1 to the left. If we want to do a very quick comparison with classical random walks in random environments, which many of you are experts in, so the first thing to notice is that the dimension is at least 2, because t is at least 1 and we are summing 1. So there will be no interpretation in terms of random walk in a potential. But the most important difference I'd like to emphasize is an advantage and a disadvantage. So the biggest advantage is a very strong ballisticity. If you are familiar with random walks in random environments, that's what you're looking for to get the majority of the results if you don't have any extra symmetry to rely on. And here the ballisticity we have is as good as it gets. So there's no single chance to backtrack in time. But the disadvantage is that we are not considering omega xt to be IID. It will be a field that will have dependencies. That's a weird way to look at, but it works in practice. We're going to give examples, more concrete examples of our random environments that usually is a Markov chain over time because it makes more sense in applications. But that's the distinguishing feature, I would say. And because of this, we are going to focus a lot of our energy talking about mixing conditions. And as it becomes clear, the better this environment mixes in space-time, the easier it will be to get results about the random walk. And that's a very pictorial description, but imagine that mixing is a one-dimensional thing we can tune. At the very end of the spectrum, we have IID, and the very extreme dependence would be just supposing ergodicity. Okay, we are always going to assume that omega is ergodic and translation invariant. So the worst case is when it's only ergodic, but in that case we basically can expect anything. There will be counterexamples for even law of large numbers for the random walk. Okay, so we start with the simplest case. If omega xt is IID in space-time, there's a very simple way to understand what's happening. You basically sample your environment and your jump at the same time at the origin, and then you jump. Now you do the same, you sample the environment and the jump at the same time, and you realize that the random walk is doing a simple random walk, maybe with a drift, under the annealed law. So you already know that the random walk is going to satisfy a law of large numbers and a CLT, but okay, what's not that simple, and it was proved by Odrini, Milos, and Pellegrinotti, is that you have a quenched CLT. Okay, so even if you freeze the environment and you say sample 1 trillion random walks and put the empirical distribution, you're still going to see a Gaussian with the same variance as this you saw for the annealed law. Okay, now moving on to the right, we have a region that we're starting to call it, we meaning my co-authors and friends, the uniform mixing region. Okay, and this is perhaps where the field got really much faster growth with a famous result by Comets and Zaituni, where they start to consider seriously dependent environments. And it starts to also dictate how things are going to progress from now on, which is in terms of the mixing condition you describe on your environment. So I will try to focus the more I can on general statements, like here is a hypothesis, here is a theorem about the random walk, instead of specific examples. And this is one such result. So what's the mixing condition they've introduced? Before I state the result, it's called cone mixing. So imagine you have space-time here, just as in that picture, and you take some event A that only depends on negative time. You could look at the whole space, but in negative time. And you have another event B that looks at a cone in the future within distance h from A. So these two events, of course, could be dependent because omega is a dependent field. But if the environment mixes reasonably, you can expect that the probability of A given B be close to the probability of A. Sorry. B given A, the probability of B. But you do require some strong condition. Let's make it very brutal here, but much better results are known already, but let's be extremely on the safe side here. So no matter what you condition on in the past, you saw some terrible stuff already in your life. If you wait for time h, you kind of forget. And this will be used, of course, when studying the random walk at a given time that you want to, refresh or renew. And under the cone mixing condition, you have a law of large numbers. Much more has been studied since then in the uniform mixing context by, okay, there are many people, Avena, Redig, and Fullerin. I may be missing more people, but okay, I don't claim that my citations are going to be complete, sorry. But now you basically have, under different conditions, but of similar spirit, a central limit theorem. So it's not unfair to say that this is a well understood region of the dependence space.
So,
yeah?
Are you calling uniform mixing region the region where you have a co-mixing condition?
No, because these other papers came up with different conditions, but I'm really talking about this symbol here. So no matter what you saw, even if it was a very small probability event, you still can have a chance to see something fresh in the future. And when you see the other conditions, you're going to see what the uniformity is about. It's really a uniformity over A. Okay, now we jump all the way to the right here, to the part that Daniel talked about in his talk, which is much more brutal, is conservative particle systems. So here, you don't have a good mixing at all. So if you saw a particle here, you know that it's going to be around. And if things are diffusive, omega 0, 0 is going to be related to omega 0 t by something like 1 over root t. So that's very bad mixing properties. Although, for most systems that have been studied, as soon as you go a bit away from this vertical dependence, say you're looking at omega 0, 0 against omega ct t, then it's already exponentially decaying. So the dependence is really aligned with the y-axis. Okay, so there is a very extensive literature on random walks on top of conservative particle systems, not only because they pose a challenge, but because there is real interest from the physical community. There has been many works on the exclusion, like Daniel mentioned, collections of IID random walks. So just imagine you start independent random. By the way, this process is, especially the exclusion, makes much more sense in the continuum, but doesn't make a lot of difference. So just imagine you have the process defined on the whole continuum of time, but you're just looking at some discrete times what the state of the exclusion was in order to decide the jump probability. And more recently, there are some works on the zero range, which is as complex as it gets for the recent techniques to work. I'm not going to make... I took note of some names, but it's impossible to make an exhaustive list. Luca Avena has worked on this, Rangel Baldazzo, Berard, Blondel, Guillaume. Okay, many people worked on this, and it's very fruitful, but I can try to summarize very poorly what is understood now. So because of this decoupling, this horizontal decoupling, when it makes sense, if you have a horizontal ballisticity as well, remember, the vertical ballisticity comes for free, but sometimes you force yourself to have a horizontal ballisticity as well, either by choosing your piece in a way that you always jump to the right more than to the left, or by taking some perturbative regime of high density in the exclusion such that you have a drift to the right. So when you have horizontal ballisticity, you have CLT. And this is under severe quotation marks because it actually only works for these two models because we can make renewals. But for example, for the zero range, there is a CLT for very extreme drifts. As soon as you have no ballisticity, say the worst case your speed is 0, then we don't even know at the heuristic level if we should expect super diffusivity or diffusivity of there's a phase transition between the two depending on the rates of the environment. So this is a very interesting open question. But I'm not going to focus this talk about that extreme of the mixing line. What I'm going to focus today is on this region that I call non-uniform mixing. Okay, of course, this is non-uniform mixing as well, but let's say fast but non-uniform mixing. So this is a region that should be pretty obvious. I mean, should be well known as this as well. I don't expect any physics surprise here, like subdiffusivity or superdiffusivity. But we don't have complete results as we have for uniform mixing yet. Yes?
Question. So, there is this work of Livellani and company, which is definitely not uniform in the sense that you mentioned. Is that following? Where does it fall? Do you know what I'm talking about?
No.
So we'll discuss it.
Yeah, I'll mention many results here. This is not an unexplored region, but this one I don't know. I have to check. Okay, so I'll start with the conjecture because this conjecture basically solves the whole thing and we could go home. And I don't expect it to first be wrong or to be unfeasible. It's just something that we don't know how to do. So first, what the mixing condition related to this question is. Take again events A and B in space-time. They are defined on boxes of side length r, and they have mutual distance at least r. You could change the mutual distance a little bit. And you take these two events, and you suppose that the covariance the supremum over AB again, the covariance between them is decaying as R to the minus alpha. And I'm going to call this condition star. You see I'm not dividing by the probability of A anymore, so this is what I mean by non-uniform. And this is known to be true for all the examples I'm going to mention, the ones we know how to prove, CLT for the random walk, and the ones we don't know how to prove. So this is an easy to check condition. And the question is, let's say you ask for uniform ellipticity as well if you want. I'm going to state here. So does star with alpha equals 100 d plus 100 implies CLT? And you can even take 1 over 100 here, if you like more hundreds. And it's very tempting to say it does, because you start to pile these boxes very near each other. You see I put some leeway here that's very much smaller than the diffusive scale. So what happens here is basically independent of what happens here and so on. So you should have CLT. Whenever I say this, I rethink my last 4 years and say, oh, was I wasting my time? There's an easy proof of this. Maybe there is. But okay, we're going to talk about what we actually know how to prove. Just one warning: if alpha is small, we have a counterexample of a random walk that doesn't even satisfy law of large numbers. So it's a dangerous terrain. Because okay, at least there is no abstract nonsense argument like, oh, this is subadditive, or then you always have law of large numbers because of ergodicity. You have to do something. Okay, and in this context, the first result I want to mention is it's because it's a general statement under this exact condition. So it's by Oriane, Hilario, and myself. So we basically say that as soon as, okay, this is restricted to dimension 1, as soon as alpha star holds with alpha equals 8, then we have a law of large numbers. No CLT. So this is nice because it's a general statement. You know, it's how things started there, so maybe soon there'll be CLT. This has been very recently generalized by Alasia. So our co-author there defended his thesis on Tuesday, and he generalized this for long range. Sorry, this is for nearest neighbor, and here he put finite long range. And this is far from a trivial extension, because you see d equals 1 and nearest neighbor is crucial because we want some non-crossing property of the random walks. So in one dimension, if they're nearest neighbor and they start from odd sites or even sites, they can never cross each other. They either merge or they don't touch. So they preserve the order. And this is crucial in the argument. And here he got away without this property. And he also generalized it to weaker ballisticity conditions. So meaning it's not really a random walk in dynamic random environment anymore. You fix a random walk in static random environment with dependencies. But you say, for example, you jump up with probability at least 1/2 plus epsilon. So now you're going up, as your drift is uniformly in that direction. So you have ballisticity, but now you don't have this non-crossing for another reason. You could go under the other walk. So still work to do. And before we move to the result I want to talk about today, let's pause a little bit to give examples, because I think I already gave two conditions, a bit too dry. So what's a typical example that satisfies the cone mixing property? That would be spin flip dynamics. Imagine that every site here in space has its own Markov chain on the state space 0, 1. Could be more general, but you know, and maybe it only flips with a very small probability. So it stays at 0 for a long time, then it flips. But okay, it mixes exponentially fast up, and because of the shape of the cone mixing property is satisfied. So what's an example that satisfies this, but not that? So there are many. The most notable one is the contact process. I'm not going to define it, but for those of you who know, I'm talking about the contact process on a supercritical regime under which you can define the the upper stationary measure. So basically what you get as a limit if you start with everyone infected. And this can introduce a stationary ergodic process that mixes very well, actually exponentially, alpha is equal to infinity. But it doesn't mix uniformly, because if you start with a whole region that is uninfected, you're going to take a linear time for the infection to invade. So these two boxes start to fill each other. Okay, and the contact process was studied, the random walk on top of the contact process was studied by Avena, Frank, and Renato. But really the big milestone here was by Tom and Eulalia, and they showed CLT for the random walk on top of the contact process, no matter the parameters. So this was a major contribution. And there are several of these, like studies that focus on a single example and manage to prove CLT, but fewer general results. A question? Another interesting example is the East model. That again, I'm not gonna, okay, maybe I can define this one. Every site is gonna have a Poisson clock. When it rings, it's gonna change its state from 0 and 1 with probability P. Just like the spin flip, but before flipping, it looks to its right, and if it's a 1, it suppresses the change. So you need your eastern site to be a 0 to facilitate your transition. And this is a process that has a spectral gap, mixes exponentially fast, satisfies the condition star with alpha equals infinity, but it's not, again, uniformly mixing, because, again, a region of 1s freezes you from transitions for a long period of time. And for the East model, okay, since we know this, that law of large numbers works here, but we don't know if we have CLT. So that's a very nice problem that we consider trying in the future. We do have one example, one situation for this model where we have CLT due to Avena, Mondel, and Alessandra, where they prove that if omega is a Markov chain in space-time that has a positive spectral gap, so this is all satisfied by this model, so we're in good shape here, but they have an extra hypothesis, P0 minus P1 should be very small, an epsilon that depends on the gap. Then we have CLT. So what does it mean? It means that you rarely have to look at the environment to decide where to jump. Usually you can decide by yourself, but sometimes you have to look at the environment. You know, if you use uniforms, there's a small interval where you are unsure. And this is a very nice work that I really like because it's the only work I know actually where not only the random walk can look at the environment to decide its jumps, but it can also alter the environment. So if the random walk from time to time decided to insert another particle in the east model, they would still have CLT, which is against all the other techniques I've tried so far. Okay, there is a more recent work by Rangel, Marcelo, Daniel, myself, where we it's full of hypotheses, so I don't have a lot of space here. But basically, if your random walk is left to right symmetric, and your random environment is FKG, something doesn't appear often in this area, and your perturbative, so since we are symmetric and perturbative, it basically means P0 is 1/2 plus epsilon, and P1 is 1/2 minus epsilon. That's a kind of symmetry. Then we have, alpha large. So we have law of large numbers because of the previous result I mentioned, but we don't have CLT. What we have is a lower bound on fluctuations. So you see, as soon as we start to break the uniformity of the mixing, some results start to be hard to state. But not today's, yes?
Do you really want to put an absolute value around your condition?
Say that again?
Do you maybe want to put an absolute value on your condition?
Oh, yes. Yeah, yes. Thank you. Or you have FKGs also. Sometimes it covers your other side direction. Several times we are looking only at the increasing events here, so the other side sometimes I forget because I get by FKG. Okay, so let's talk about today's result. We start by defining a new renewal condition, mixing condition, that at first may look a bit artificial. I'll try to justify it later. So we have cones. Instead of just one cone like in the cone mix, we have two, the past cone and the future cone. We're not going to add events A and B. We're going to look at the sigma algebra, F minus and F plus. What are they? F plus is what you expect, the sigma algebra of the environment, where xt belongs to the future cone, but F minus is more subtle. Look puzzle. F minus is different because we actually need to build the second environment. So we have this environment already, right? So we need the user of this theorem to define a second environment that's also ergodic, also translation invariant, also 0, 1. And F minus can also look at the second environment. And this is what we call the environment of traps. And I'm going to explain what they mean right soon. So you have here your space-time, and not only you have the omegas deciding your probability, your jump distributions, but you have environment of traps. Here I'm marking when eta is 1. And they don't affect the random walk at all. Okay? but they are necessary for the condition I want to talk about. The condition, I'm going to call it, lack of a better word, double star. For every omega in F plus, so I'm looking here at the event in the future, the expectation of omega given F plus, given F minus, is the expectation of omega given eta 0 if eta 0 is 1. So here I'm centered at 0. Everything is translation invariant. So what this condition actually means is a kind of a Markov condition. The expectation of the future conditioned on the past is equal to the expectation of the future, period. But okay, this only holds when I'm on a trap. So it's like you sprinkled renewal space-time points in your environment. If you step there, your environment renewed, kind of miraculously. Okay, I don't think I should use this a lot because it's blocked, right, by people there. Is it okay? Okay, so this condition, as I said, at first sounds a bit...
So that's more as a definition of the trap statements.
Yeah, you should find eta such that this holds. And then the theorem is that under, so suppose that double star holds, and also that both omega and eta satisfy star with alpha bigger than 1. Then we have law of large numbers. If alpha is bigger than 2, then we have central limit theorem. Which is nice because these are supposed to be the sharp things indeed. So before I go to the more details in the result, I wanted to first compare the Holy Grail hypothesis star with the weird looking hypothesis double star. So there are several ways to prove star, but one of the most used ones is through couplings. So you have your environment in space-time and you define it through some graphical construction. And suppose that at some time here, preferably right after the bottom box, you explore two independent environments, omega and omega prime. Now that they ran independently until here, you switch on the coupling where they're going to read the same graphical construction. So they start to couple. And if they do couple before the box B, you're basically successful and you proved this star condition. And this alpha is related to the probability that you manage to couple them before the box B arrives. So this type of coupling is used to prove star, is also very useful proving double star. So that's the advantage of double star. It's not that different from this in this case. Why? Because you just, put here times 0, put W and W prime in the negative cone, switch on the graphical construction, and if you're lucky, they couple before touching the future cone. Of course, there's some luck involved here in the tip, but you don't mind because we don't want the probability to find the trap to be high. We just want to be positive. Okay, so the two conditions are not extremely different when you have this type of graphical construction coupling. The problem is, for example, in the East model, We know that it satisfies this not because of the graphical construction, which we don't understand at all, but because of the spectral gap. When you have this condition for something like the spectral gap, you are completely hopeless to prove this. At least we tried, but didn't manage. Actually did a simulation of this model with a natural coupling, and it looks very obvious that this holds. But, you know, how to prove it? Okay, what are some concrete examples for which we can prove double star? One very nice example is Boolean percolation. Just start with a Poisson point process in the plane. You know it's continuum, but then we're going to read only on Z2. And for every point, you put a ball of random radius, and you assume that the radius satisfies some tail assumption like this. Then this process satisfies both the star and double star condition. So your random walk here, although sometimes it feels a drift in the balls and a drift in the other direction in the empty regions, it does satisfy a CLT. And what's the proof that this satisfies the double star condition? You basically look at the origin here and you say that eta is 0 if no ball that touches the future cone touches the past cone. If this is true, then you say eta is 1. Sorry, you decoupled. And now I have to prove this thing here, but it's doable. So these are decoupling times. Another example is renewal spin flips. So for example, I mentioned spin flips as an example of uniform mixing, where every site has a Markov chain on 2 states. Imagine that this Markov chain that every site has flips according to a renewal time for which the inter-arrivals satisfy a similar hypothesis. So if these renewal times are short-tailed enough, you do satisfy the double star condition, and you have CLT. The proof of even the definition of eta in this case is more contrived, but it's actually okay. Another example, I'm going to stop examples, but it's a finitary factors of IID fields. So for those of you who know, it's not a very nice class of dependent environments. So I managed to prove the CLT. Now in the last, 5 minutes? 10 minutes?
12 minutes.
No, I think the last speaker has the obligation to finish early. So I'll give some idea of the proof. Okay, so when I start to talk about the proof, you're going to say, you can stop, it's trivial, let's go on. But then I'll hold you for 5 more minutes. So you have this eta field, and I'm going to always work on the measure P tilde. That's basically the original measure condition that eta is 1 at the origin. It doesn't change anything, it's a positive probability event. And the random walk is doing its thing, but sometimes it falls on traps. So tau 1 is going to be the first time after 0, such that it falls omega of x tt is, eta is 1. So the first time it falls on a trap, easier to say than write. Tau 2 is the second time, and so on. And the first thing you prove is x tau I minus x tau I minus 1 as a sequence is IID. Even with the times as well. So these arrows here are IID. Okay, so that does it basically. Now all we have to do is to find a bound on tau 1. So if we have first moment of tau 1, we get law of large numbers, we get second moment of tau 1, we get CLT. So that's the moment I'm sure everyone wants to go home. But okay, a few warnings because we worked a bit, so I have to justify the money Brazilian government paid me. So the most important thing to notice here is that this would be indeed a trivial proof if f plus and f minus, which I just erased, so we have the cone in the future and the cone in the past. And in the past, I looked at both omega and eta. In the future, I only looked at omega. And I said the future condition on the past is fresh given that eta is 1. But I did not include eta in the future. If I had included eta in the future in my definition of double star, this statement would be trivial. But then I wouldn't be able to prove any example. Actually, we have hopes that this would work, the Boolean, but yeah. You see, it's very important that you don't ask for information about eta in the future. So this first thing changes this step of the proof. So we have to be very careful and resample the scenes in certain ways. It's delicate. And the second is also seemingly quick because we're walking among a density of traps. So we're going to fall into them actually very fast, right? Do expect even more than second moment. So why is it that it could be hard to prove this? So we don't know anything about random walks, right? We're trying to prove CLT. So if we knew it was a simple random walk, of course it would fall in the traps. But we don't know anything yet, we're trying to prove. So how do we show something that we don't know how to behave fall into traps? So the only way we know how to prove this is show that any Lipschitz path that you create in your mind falls into traps. So that's a brute force. But now you're in trouble because these traps are sparse. So it's not clear. I mean, probably the opposite is true now, right? You can probably avoid them. They're not a blocking set. Okay, but remember we had some uniform ellipticity that I forgot to state. So actually falling in the trap is not strictly necessary. If you fall in some cone around the trap, after which a few, like this constant length, after you stepping into it, you can fall into the trap with positive probability, then you're done. And as you increase the size of this cone, this becomes a blocking set. So it's kind of a percolation argument, you know, for this expert. This is our perturbative parameter. We're going to use renormalization. This hypothesis is going to be very handy. And the only thing that for the specialists, again, that's a bit worrying is that as we increase L, we also increase the dependency. Because, you know, this is part of the environment now, this whole triangle. But it's perfectly possible to get by. And that's it. Thank you very much for your attention.
Questions?
I want to be. So I noticed, I guess, in your models and also Daniel's as well, it's where your law is dependent on where you are. Do you know, do you get anything, or have you ever considered, it depends on where you're going?
So usually it's not a big problem. Usually you can do this by basically taking every possible place you could be going to as part of your environment at that point. So that point has a little booklet telling you, this will increase the dependence of your environment, but okay, if it's a finite range, it doesn't change anything, doesn't break star or double star. If it starts to be heavy-tailed, then it's a problem because even the jumps being heavy-tailed, sorry, not even heavy-tailed, infinite, but light-tail, we didn't think much about it.
People study the large deviations for random walking with dynamic environments.
So we have a very bad habit of calling, me and two other people, calling concentration large deviations, which is a terrible habit. That I'm aware of, no large deviations have been studied, but we know concentration. So we know that, of course, the concentration cannot be much better than the alpha there, raised. So if your environment is alpha dependent, you can go away of your law of large numbers with probability 1 over r to the alpha, but this is proved.
If you take a diffusive environment in higher dimension, is that also among the examples?
I wish no. I think if you take what we probably can prove is that if your particles in the diffusive environment they don't quite conserve, they disappear after a renewal process, which is much better than disappearing with an exponential time, then yes, if your renewal has, say, light tails, that could be a way to try to push through.
So is there,
Yeah, so maybe a basic question. So is it useful to think of the cone ahead of the traps, and you look at past, because once you enter a trap, there's non-zero probability of leaving it. So can you look at the cone ahead of the trap and see the past emerging from the trap? That helps them so that informs the logic.
Yeah, maybe it's possible to.
So you don't need information from the future, but you look at the cone of the trap, you look at the line base of this cone, and look at all paths emerging from the trap. So that line.
Yeah, I think if you emerge from that future cone, maybe you can prove that you had a positive chance to have been in the trap before. That could be an alternative proof, but maybe it's a bit harder to prove because you already have some other information.
okay, so if there are no further questions, then let's thank Augusto and the previous speakers of this